So just one announcement before we get started. So hopefully everyone saw the email from the TA. So if you have, course questions, please, come to my office hours, the TA's office hours, and talk to us about things. We're happy to help you work through, any of the problems on the homework or, anything, related to the course. If you struggled a bit with the first homework, and in the end that you didn't kind of figure it out, come talk to us. We're happy to help you get through the course material. Make use of us. It's really what we're here for. I think that's it announcement wise. So that the second homework will be out this evening. I'm basically done with it, and I'll send an email letting you know when it's out and when it will be due. Okay, so let's pick up where we were last time. So we were finishing up some discussion about duality. So we saw an example of another nice property that we get when there's zero duality gap called complementary slackness. So what complementary slackness says that is if there's zero duality gap and you're at an optimum of the primal and the dual problem, then for every one of the Lagrange multipliers that corresponds to an inequality constraint, either that Lagrange multiplier is greater than 0, or the inequality is strict. So I just wanted to revisit one of the slides I had from last time. Maybe if my my touchpad will work here. The pen works, but my finger is broken apparently. Oh, there we go. Spoke too soon. I just wanted to revisit one of the examples that we saw last time, just because it was messed up on the slide, and I just wanted to point it out, the correct formulation this time. So we saw this example last time, the last couple times, of projecting a point P onto a set of box constraints. So here the only constraints are inequality constraints. And when we formulate the Lagrangian for this problem, right, we have a sum of Lagrange multipliers times our lower bound constraints, plus a sum of Lagrange multipliers times our upper bound constraints. And what complementary slackness tells us is that either the constraints, these inequality constraints, are met with equality. So that is that either xi is equal to its upper bound or xi is equal to its lower bound, or the corresponding Lagrange multiplier is 0. So written here correctly on the slide this time says that if mu I is greater than 0, complementary slackness tells us that the product of mu I times xi minus ui has to be 0, right? So that implies that xi has to be equal to ui. Similarly, if lambda I is greater than 0, then xi has to be equal to li, right? So what that says is that if the Lagrange multiplier for that constraint is positive, right, then the constraint has to be satisfied with equality. Right? Conversely, right, if the constraint is not satisfied with equality, right, so if, for example, xi is less than ui, then it must be that the corresponding Lagrange multiplier is 0. And we did another example of this in class, but I it was messed up on the slide, so I just wanted to point it out, kind of correctly this time around. Yes, this is only true, right? This is only true for when you have a pair of optimal solutions, right? So it's not true for anything feasible and anything that's primal feasible. It's only true for the optimal, for some optimum of the primal and some optimum of the dual. Okay, and we did some other examples last time that I don't want to go into again today. And then we finished up with a set of necessary and sufficient conditions for the x star, lambda star, and nu star to be primal and dual optimal solutions in the case that there's zero duality gap, so-called KKT conditions. I think where we had stopped was showing that for some problems, the KKT conditions can actually lead to sort of simple solutions. In particular, for this quadratic condition problem, we saw that if we just write down the KKT conditions, it gives us a linear system. And we could just solve that linear system to find the optimal x star and nu star in this example. Right. Okay. So we've seen a lot of things. We've seen a lot of different examples of duality and a lot of different properties. What I wanted to do today was, one, show you how some of this stuff works, like algorithmically, right? Like how do we optimize the dual and things kind of related to that. And I also wanted to do some more examples and talk a little bit about like where all this stuff goes wrong and just some general sort of tricks or observations about constructing duals and some related thoughts. The reason for doing this is that it turns out that constructing these dual optimization problems is actually a very delicate process in some sense. It very much depends on the formulation of the problem that you pick. Different formulations will have different duals. Some of them will be good and some of them will be bad. So I'm going to give some examples of good and bad ones in a second. But it's worth kind of keeping this in mind because when you go to apply some of this stuff in practice, it really kind of does make a difference which formulation you use. So my hope is today, so we've seen a lot of different examples. So my hope is today to go through some simple examples and illustrate the concepts, kind of clearly. And so hopefully, all of you can kind of help me out and go through these things rather than just me, doing them myself. One, because you're going to have to do it on the homework, and two, it'll help just to make sure that we're all kind of following along and get the process. Didn't we do this right at the end of last time? If we didn't, I'm happy to go through it again. And maybe we can just do it very quickly. If we stopped right here, I can't remember. I thought maybe I had done it, but if I haven't, let's just do it really quickly. So here's a simple quadratic minimization problem. In fact, it's an example of a quadratic programming problem because we have a quadratic objective function with subject to a linear constraint. Slater's condition tells us that there's zero duality gap here as long as there exists some x such that ax equals b, and q is positive semi-definite. Right, so we need the objective to be convex. That's this positive semi-definite thing, and there has to be some feasible point. And then Slater's condition will tell us that there's zero duality gap. So since there's zero duality gap, right, we can apply the KKT conditions to find a characterization of the optimal solutions. So it doesn't always work out so nicely, but in this particular case, the KKT conditions tell us, well, we need to have the gradient of the Lagrangian at the optimal point with respect to x. All right, evaluated at that point should be 0, and that all of the primal equality constraints have to be satisfied. These other conditions don't apply because the other three conditions, complementary slackness, dual feasibility, and primal feasibility for inequality constraints don't apply because we don't have any inequality constraints in this case. All right, so putting this into context, that tells us that the KKD conditions tell us that we need the gradient of the Lagrangian to be equal to 0 at x. So what we would need is we need to find an x star, lambda star, and nu star such that the gradient of the Lagrangian. So the Lagrangian in this case is 1/2 x transpose qx plus c transpose x plus, right, sum over all I of nu I times the sum over all j of aij xj minus bi. So constructing the gradient of this thing with respect to x, we get, which I'll denote this way, right? And evaluating it at x star, nu star, some optimal point, we would get this is equal to, well, the gradient of the first piece is just q times x star plus c plus the sum over all I of nu I, and the gradient of this term just looks like so when we take the partial derivative with respect to xj, it just pulls out a single element from these pieces, from this thing. So what we end up with is the sum over j of aij xj minus bi. That derivative, it's like the derivative of a times x minus b, right? So it's a linear function, so the x part will disappear, right, when we compute the derivative, and we're just left with the sum over all I, sum over all j, of this, of nu I times aij, right? Which we rewrote in it's really like this, sum over all j of, yeah, I guess that's it. But it's more like I have to stick it in a big vector. This is where I was using that like funny notation last time, and I'm trying to avoid using it because some people didn't like it. So when I take the partial derivative with respect to xj, right, I get the sum over all I of nu I times aij, right? So I stick these things into a big vector. This big vector looks like a transpose times nu, right? And I should put a little star here because I'm evaluating at the optimal. So the gradient looks like q times x star plus c plus nu star times a transpose, right? Because I take nu star to get the jth component, I take nu star and I multiply it by the jth row of a transpose, which is the jth column of a, is what I get from the partial derivative. So that's the first condition from KKT, and the second condition tells us that at the optimal it should be that a times x star is equal to b. That's what the KKT conditions tell us, right? I set this thing equal to 0 because the gradient should be equal to 0, and I just rewrite that as a linear system, right? So some function of x star and nu star has to be equal to some constant, right? And then some function of x star has to be equal to some constant b in the second piece. So regrouping those terms together, I get a linear system looks like this. I've written it sort of in this block matrix form. So what I mean by this formulation is if I take x star and do like sort of the standard matrix multiplication, right? So I take x star times q and nu star times a transpose, I should get minus c. And I get that just by rearranging this equation, right? This equation 1. I got q of x star plus c plus a transpose nu 0, right? So I just move c to the opposite side. right? And then sort of rewrite that in sort of a block multiplication form. Writing things in this block multiplication is a pretty standard thing to do with matrices. The only thing that you need for this to make sense is that, right, like these individual components of these vectors have to be the right size to multiply times the other matrix, right? So as an example here, right, x is in an n-dimensional vector, right? So it better be that this first thing is in Q better be an m by n matrix, right? So that I can multiply x by it. But that's true. Q is an n by n matrix, in fact, so the multiplication makes sense. Same thing for A. A is an m by n matrix, and nu is an m-dimensional vector, right, where m is the number of constraints in the system. The point of the reason for pointing this out is just to say that, like, there are some times where, like, this set of necessary and sufficient conditions itself can just be solved directly, right? It just gives a linear system, and you just solve and get some solution. That solution can be found basically without solving an optimization problem, right? There's no need to even construct any duals or anything here, right? You just solve this, or do gradient descent or something. You just solve the system. Okay, good. Questions about this example, other than probably this kind of mess of matrix algebra. We've seen it a couple times now. It's just one of these unfortunate things about writing down. If you don't have a ton of comfort with matrices and vectors, you should go back and convince yourself, for example, right, that the gradient of x transpose qx is actually equal to q times x. There would be a 2 in front of it if there wasn't a 1/2. But you should double check those things yourself, right? You can write it out sort of like really painfully explicitly, take the derivative and then just see that that's what the answer is. But we've seen that a couple times now, so I'm not going to go through that. Okay. So, like I said, I wanted to do a couple of sort of simple examples that sort of illustrate, where some of the theory breaks down, and things that you should be aware of and be comfortable with when you're working with these dual problems. For this, I picked some much simpler optimization problems to illustrate. So, like I said, hopefully we can go through them together and all kind of be convinced and happy that they're illustrating what I claim to illustrate. So I picked these examples to illustrate some in addition to illustrating some things that can go wrong with the convex optimization. I also picked them to illustrate some of the things that you might encounter during the process that we haven't seen as part of some of the examples that I've done so far. So what can go wrong? So I think I mentioned a couple things. The first is that the dual function could just be equal to minus infinity. In this case, I would say that the dual is degenerate, right? It gives you a lower bound on the primal function, but negative infinity is a lower bound on everything. So that's not really interesting. There could also be a really large duality gap, or just a duality gap at all. In such a case, right, solving the dual doesn't necessarily give you a solution to the primal problem. Though I'll talk a little bit about it later on. Sometimes you can take problems that have a relatively small duality gap and turn that into an approximation scheme. In fact, this is a strategy that's been used a bunch in practice to design approximation algorithms. Okay, let's see some of these simple examples. So the first example that I want to do is an example of a situation where you end up with a degenerate dual. So there's lots of different ways that you can end up with that. So in this particular example, I've selected an optimization problem that is not a convex optimization problem. Right? So you'll notice that the objective function here is a concave function, and I'm trying to minimize a concave function, which is not a convex optimization problem. right? If I was trying to maximize a concave function, right, then its negative would be the minimum of a convex function, which would be fine. But here, there's no way to put this into, there's no way to transform this problem into a convex optimization problem. Despite that, this problem is well defined because the optimization is being done over a bounded region in space, right? So in the xy plane, I've just carved it up into -1, 1, and -1, 1. So we're just talking about this square of possible solutions, right? So we're looking at trying to find the minimum value of this quadratic function over this square, right? The only drawback here is that this quadratic function is not convex. So as an example, right, Slater's condition wouldn't apply here because although there is some point that's strictly feasible, right, so there is something inside the square, so someplace where all the inequality constraints are strict, the objective function is not convex. So Slater's condition, right, one of the constraint qualifications we saw last time, does not guarantee that there's zero duality gap for this problem. And in fact, the duality gap is garbage. To see that, let's just construct the dual function. So, so to do that, right, we just apply the standard method of Lagrange multipliers. So I guess because I want to make it a little more interactive and just to make sure all understand, how to do this, I guess I'm going to write down the Lagrangian function. How many Lagrange multipliers are there in this case? Got a vote for 2, 4. More votes for 4 than 2. So someone that says 4, why do you think there are 4? That's right. So there's always one Lagrange multiplier for each constraint. So one of the 2s has been convinced. There's one Lagrange multiplier for each constraint, right? And so each one of those 2 lines up there actually is 2 constraints. So there's 4 Lagrange multipliers. So when we go to write down our Lagrangian, right, it's a function of x, y, and these 4 constraints. I don't know, let's use lambdas for the lower bounds and mu's for the upper bounds, let's say, right? So the Lagrangian looks like this. It's minus x squared minus y squared plus, lambda 1 times, well, x has to be greater than or equal to -1, but we have to put it in standard form. So it's -1 minus x has to be less than or equal to 0. And then we have plus lambda 2 times -1 minus y, again, putting it in standard form, plus mu1 times, again, we have to have x is less than or equal to 1, which is the same thing as x minus 1 is less than or equal to 0, and mu2 times y minus 1, because y less than or equal to 1 is the same thing as y minus 1 less than or equal to 0. Okay. So this is our Lagrangian, right? Now to construct the dual optimization problem, right, we would minimize this thing over x and y squared. Now it's not a concave optimization problem, right? So, I mean, it's not a convex optimization problem, right? Because minus x squared minus y squared is not a convex function. So I can't necessarily just take derivatives and solve, right? Because now there could be multiple critical points or something, right? And I'd have to check them all. In this case, right, if I was trying to minimize this thing over x and y, what is the solution? Vote for -2. I will agree that that's the solution to the primal problem. but it's not the minimum of the Lagrangian for a fixed lambda and mu. What's the minimum of the Lagrangian? So let's say, just fix lambda and mu to 0, right? Or something, right? What's the minimum of the Lagrangian then? So maybe let me write it down while you're thinking about it, right? To get the dual function, which is a function of the Lagrange multipliers, right? I have to take the infimum over x and y of L, x, y. So what is this thing? Right. Yeah. So again, right, just like the previous comment, right? Yeah, it is true, right, that that's where the minimum of the primal problem is, but that's not the minimum, right, of the Lagrangian. Yeah. It's not even the argument necessarily of the Lagrangian, right? It's because the Lagrangian is an unconstrained optimization problem, right? I'm just literally trying to minimize it over x and y. So we have a vote for negative infinity. Any other votes? Okay, so the answer is indeed negative infinity. To see why that's the case, we just look at this formulation here. This piece over here is linear in the x's, but it doesn't matter what this linear piece is. It could be some really complicated thing, right? As x gets large, the quadratic term will dominate, right? I mean, that's basically what happens sort of asymptotics, right? This is like big O notation 101. This function, right, is not necessarily increasing or decreasing in x or y, but certainly as x gets large, it gets arbitrarily close to negative infinity, right? So as an example, right, just let x run off to infinity. It doesn't matter what this term is. This first piece will dominate because it's a negative x squared. It's running to negative infinity, right? So if I make x large enough, I can drive it to negative infinity, no matter what. The same thing's true for y, but it doesn't really matter, right? Because if I can drive it to negative infinity just with x, that's the solution. So in fact, the dual problem in this particular case is just equal to negative infinity. That's it. That's the dual. That's not a very interesting dual, right? And it wasn't supposed to be, right? This is supposed to be an example of a degenerate dual formulation, right? The reason I'm doing this example is to point out, right, one, right, you can easily end up with situations where the Lagrangian can run off to negative infinity, and this is sort of the worst case that can happen, right? It runs off to infinity everywhere, right? It doesn't matter what value of the Lagrange multipliers you plug in, the thing always returns negative infinity. So it's just not even an interesting function of lambda and mu. Okay. So I'm going to pause here for a second. Are there questions about this example? Does everyone see why the minimum is negative infinity? Okay, I'm going to judge by your silence that there are no questions. So like I was saying when I mentioned before we did these examples, right? Sort of one of the weird features of this duality thing is it really does depend on the presentation of the constraints. So I'm going to just slightly tweak this optimization problem. I'm going to write it in a slightly different form. It'll be the exact same problem, right? It'll have the solution. It'll have the same set of constraints. I'm just going to specify them in a different way. And when I do that, it will magically turn out that the dual is no longer sort of as degenerate like it is here. So let me do that. So here's an example. All I did was all I've done here is replace the x less than or equal to 1 and greater than or equal to -1 constraint with x squared has to be less than or equal to 1. These two constraints are obviously the same, right? Right. It's a different way to write that constraint. However, when I construct the Lagrangian for this problem, I'll end up with a different dual because the Lagrangian will be different, right? Because it's a different function, right? In particular, right, now there's only 2 inequality constraints for this problem. So the Lagrangian only has 2 Lagrange multipliers. So let's write it down and see what happens. All right, so the Lagrangian in this case is a function of x and y, and lambda 1 and lambda 2. That's equal to minus x squared minus y squared plus lambda 1 times x squared minus 1 plus lambda 2 times x squared minus 2. And then the dual function is a function of lambda 1 and lambda 2 that I get by computing the infimum of the Lagrangian over x and y for a fixed value of lambda 1 and lambda 2. All right, so what is the dual function in this case? Again, take 2 seconds to think about it, and then I'll ask. It does depend on the value of lambda. That's a good point. How does it depend on the value of lambda? Oops. And that's the wrong. I'm just writing random things up there. It should be a y squared minus 1. If lambda is 1, it goes to 0. Right, so let's see. So you mean lambda 1 and lambda 2 are both 1, right? Then if I plug lambda 1 and lambda 2, both 1 in, the x squared cancels the x squared, and the y squared cancels the y squared, and I'm left with minus 2. Right? So if lambda 1 equals 1 and lambda 2 equals 1, the answer is minus 2. Which of course is the solution to the primal problem. So that's sort of the optimal solution for the dual. But let's construct the full dual problem. What does anyone see what the full dual problem is? Well, it might be a little difficult to articulate in the chat, but yeah. So let's take this first observation. So the observation in the chat is if either the lambdas is less than 1, it's still minus infinity, right? So let's check that really quickly, right? If either the lambdas is less than 1, so of course all the lambdas have to be greater than 0. So if they're greater than or equal to 0 and less than 1, then when I add lambda 1 x squared minus x squared, I still end up with a minus something, right? It's still some negative x, it is some negative constant times x squared, which is again a concave function, so it'll be negative infinity. And so let's write that down here. So the answer will just be negative infinity if lambda 1 is in 0, 1, or lambda 2 is in 0, 1, right? So if either one of the Lagrange multipliers is in that range, the solution is negative infinity. And if we're not in that range, so we just saw that if lambda 1 equals 1, then the answer is minus 2. What about other lambdas that are greater than or equal to 1? Oh, I guess it was, someone already posted it in the chat. So if lambda 1 or lambda 2 are greater than or equal to 1, then rewriting this expression up here, right? This looks like, right, lambda 1 minus 1 times x squared plus lambda 2 minus 1 times y squared, right, minus lambda 1 minus lambda 2. Right, so if lambda 1 minus 1 is a positive number or greater than or equal to 0, and lambda 2 minus 1 is greater than or equal to 0, then this is a convex function, right? But it's just a quadratic, and in fact, its minimum is just attained when x squared is equal to 0 or y squared is equal to 0, right? So in the case where lambda 1 is greater than or equal to 1 and lambda 2 is greater than or equal to 1, the solution is just minus lambda 1 minus lambda 2. Okay, so that's the dual function. You can see, right, just like the previous case, right, there are some choices for lambda, right, for which the dual function, right, takes on a value of minus infinity still. This is actually something that happens quite frequently. It didn't happen in any of the examples that we saw, because in those examples that I did in class earlier, right, when you took the derivative and set it equal to 0, there was, it was a convex problem you just solved, right, and you just plugged in and we got a solution. The way that we interpret these negative infinity things is that, well, we know that the optimization problem in the dual will be maximizing. The maximum solution can never occur at a place where the dual function takes the value negative infinity, unless the dual function takes the value negative infinity everywhere, right? If there's even one place where it takes a finite value, then that's going to be larger than negative infinity. So typically we would rewrite this to say that the dual problem is actually equal to the maximum over lambda 1. Oops. I guess we can zoom in too. Maximum over lambda 1 and lambda 2 of minus lambda 1 minus lambda 2, subject to the constraint that lambda 1 has to be greater than or equal to 1 and lambda 2 has to be greater than or equal to 1, right? We can just implicitly impose that constraint, because if that constraint is not satisfied, that the solution is negative infinity. So these places where we get like negative infinities when we take the infimum of the Lagrangian will turn into constraints in the dual problem. Of course, we can see now that right, when I plug in lambda, the maximum of the dual, right, the dual is a monotonic decreasing function, right? So that means I can make lambda 1 and lambda 2 as small as possible. The smallest I can make them is 1 and 1, which tells me that the minimum of the dual can be is minus 2, which is indeed the solution to the primal problem. So instead of having a degenerate dual function, right, like we did before, where the dual was just negative infinity, if I rewrote the constraints just slightly, I in fact get that there is 0 duality gap for this formulation of the problem. Right? The first time you see something like this, it might be a little like, like mind, numbing in that, like, wow, it really depended on the way that we formulated this problem, right? And this is just a general feature of these dual problems. It very much, like, the dual will very much depend on how you specify the constraints. Different ways of specifying the constraints or different ways of expressing the optimization problem will result quite likely in different dual optimization problems, because the method of Lagrange multipliers is very dependent on the way that you actually formulated the constraints, right? In particular, what made this work here is that, I have a quadratic objective, so if I have quadratic constraints, right, they can cancel each other out in some places and prevent it from just running off to negative infinity. Good. Questions about this example? Again, it's a relatively simple example, but it just serves to illustrate some of the things that can happen in more complicated, scenarios, right? Where there's, places where the, things run off to negative infinity, et cetera, right? So this is a little different than what we were doing before, straight up taking derivatives and solving. Right here, we had to do just a little bit of, like, use a little bit of algebraic reasoning to figure out, right, what the solution is. No questions? Okay, let's move on to do another example. So here's an example that has a duality gap. Again, I selected this example because it's relatively easy, but this is a really dumb way to formulate this optimization problem, right? So here we're trying to minimize e to the minus y subject to the constraint that x squared plus y squared is less than or equal to x. Right. The reason that this is particularly dumb is that if you reformulate this constraint, right, this is the same thing as saying that x squared plus y squared should be less than or equal to x squared, or equivalently that right, y squared should be less than or equal to 0, right, or equivalently, right, that y is just equal to 0. So this optimization problem is dumb, right? I mean, the solution is literally just, plug in y equals 0. I'm doing this, though, to show that, again, right, you put in this weird constraint, I formulate the Lagrangian, right, and the dual problem is dependent on the way that I formulated the constraint. I might not get a nice dual when I formulate the constraint this way. Okay. So again, I'm constructing the Lagrangian for this problem. It has one inequality constraint, so I need one Lagrange multiplier. So the Lagrangian is a function of x, y, and one Lagrange multiplier, let's say lambda, and it's equal to e to the minus y plus lambda times the square root of x squared plus y squared minus x. Again, because I need to write it into the form, some function of x and y is less than or equal to 0. So I can ask the same thing. What is g of lambda, right? What is the dual function in this case? And you'd say something like, now that you're all experts at constructing these things. Any thoughts? If lambda is equal to 0, right, then the second term disappears. So we just have to take the infimum of e to the minus y over all y. I agree, right, that as y goes to infinity, then, right, positive infinity, right, this thing goes to 0, right? So let's do that. So it's 0 if lambda equals 0. Okay. What about if lambda is greater than 0? Possibly. It might depend here, right? It's possible that it depends on the value of x. I mean, on the value of lambda, right? If you set y equals 0, then the value is 1. Sure. Okay. So right, because the square root of x squared, right, would be like absolute value of x, right? So it'd be like absolute value of x minus x, right? If we were minimizing that, then I think the solution would be 0, right? Right. You should pick, x equal to the right. I guess so that's a good observation that was just made, right? If you said y equal to oh, I see, you're saying it's 1 because you plug in the y equals the y equals 1 over the e to the 0 gives you 1. Yeah, so that's the smallest you can make it. Yep, I agree with that. Square root of x squared, right, plus y squared minus x has to be greater than or equal to 0. And the first term has to be greater than or equal to 0 too, right? The question is just where does the minimum actually occur? I guess, is it possible to make it equal to 0? Yeah, it's not. I don't think it's possible to make it equal to 0 here, right? Unless lambda is equal to 0. We could work it out, right? So the again, I wanted to do this as an illustration, right, of a situation, right, where it's sort of not as trivial to do this, right, to solve this as it was in the previous examples, right? We can work it out, right? E to the minus y is a convex function, right? So is square root of x squared plus y squared, right, minus x, right, assuming that lambda is greater than or equal to 0. Right, we could take derivatives and solve, and we could see what the actual solution is. Right, it might not have a nice closed form like it did before. Right, but we could do that and solve the problem. Right. The problem with all of these examples, right, is that like constructing the dual, it can be a bit trickier than it might appear, right, normally, right? Like it's not necessarily always so trivial, right? Like it was in some of the examples that we had seen before, right? Like we actually, there's an actual amount of thinking and work that needs to be done here, right, in order to solve this in order to construct the dual in this particular case, right? And in the previous cases too, right? Like we needed to use some extra reasoning beyond what was beyond just sort of taking derivatives and setting things equal to zero, right? It requires extra work. There's not sort of nice closed forms, right, that we can just plug in and get the answer. All right. Given that no one sees the solution, this actually might be a fun thing to put on the homework. So maybe I'll just leave it like this. Another reason for leaving it is there's only 20 minutes left, and I wanted to cover some algorithmic stuff today too. So we'll leave this as a hanging, interesting example to compute the dual function. Before I talk about algorithms, I did want to do one other quick example of something that we haven't really discussed in these dual formulations yet. This little trick that I'm going to show you here very quickly, and then talk about algorithms, is actually pretty useful practically. So if you've been following along, you'll see that the book does uses some funny extra notation when it talks about convex optimization problems. It allows you to restrict what it would say, like the domain of the functions that are involved, right? So it might say things like, minimize over x in some set q of f naught of x, right? And then blah blah blah, right? Subject to some set of constraints, right? Where q is just some fixed set, and it's supposed to be a convex set, right? If you want it to be a convex optimization problem, but otherwise it's generic. One thing that's nice about the method of Lagrange multipliers is that if for some reason some constraints were easy to optimize over, you can keep them when you form the Lagrangian problem. So what I mean by that is as follows, right? And that's sort of like, kind of keeping this domain constraint, and then the Lagrangian is just the infimum over x and q, right? So you don't ever encode them as constraints. You're assuming that you can solve that optimization problem easily when you construct the dual. So here's an example of what I would mean. So here we have a problem with n variables and n+1 constraints, right? So there's one constraint for each of the x's has to be greater than or equal to 0, and a constraint that says the sum over the x's has to be equal to 1. It turns out, though, that this x greater than or equal to 0 constraint is actually a little bit superfluous when you write down the Lagrangian. So because the derivative, the Lagrangian will always be a convex function, it's easy to check that that x log x is a convex function when all the xi's are between 0 and 1, which they would have to be for this to sum up to 1, and with the sum to 1 constraint. It's convex beyond that, but you have to be careful, right? It's not really defined, right? Xi log xi isn't really defined whenever x is one of the components is less than 0, right? So it doesn't really make sense to write down the Lagrangian, and in this particular case, right, for x's that are negative. I should point out that when x is 0, we actually do define this thing to be 0. So 0 log 0 is defined to be 0 because it's the log of 0 to the 0. And by definition, 0 to the anything to the 0 power is 1. So log of 1 is 0. So it's really just the plugging in x that are less than 0 that are a problem. So when we formulate the Lagrangian in this case, we can kind of cheat. We don't have to add a Lagrange multiplier for the x for the x greater than or equal to 0 constraint, because it doesn't even really make sense to write down the objective function in that case. So we add just a single Lagrange multiplier here, new, right, and construct sum over all I of xi log xi plus nu times 1 minus the sum over all I of xi. And when we construct the dual function, g of nu, we define it to be the infimum over the Lagrangian, right, over all x greater than or equal to 0. And in fact, actually, if we just take the derivatives of the Lagrangian, set them equal to 0, and solve, we'll find that the solution is always attained at a value of x that is greater than or equal to 0. So it's easy to construct the dual function in this case. So the point of this is sometimes this is a really useful trick in practice. If some of the constraints are very easy to optimize over, you don't need to include the constraint set and add a Lagrange multiplier for them, right? You right, optimize over them when you construct the dual function. So this is useful in a bunch of places. This is a good example, right? In fact, we could redo that. We could do this whole problem where you add a Lagrange multiplier for the x greater than or equal to 0 constraint, and then solve. It just makes a mess. And you know, that's maybe another exercise for you at home to do. It makes a huge mess. You still end up with the same dual function essentially. It's just a really, really, really long, messy bit of algebra, right? Whereas if you write it this way, you just need to take a derivative set equal to 0 and basically solve for x. You get a closed form solution for xi in terms of nu, and you just substitute in to get the dual function. Okay. So those are just a couple different examples to showcase some of the difficulties or the nice properties that you know, or nice tricks you can take advantage of, and in order to you know, construct some of these tools, right? Either to make it easier or harder. If you're having difficulties doing it, you can always try to modify the constraints a little bit to improve things. So there's a question, we can do this because the domain of log x is greater than or equal to 0. And the answer is yes, but you could have substituted any constraint in here that you wanted, right? The x greater than or equal to 0 constraint is a good one to pick, right? Because you know, the objective function is only defined, right, over that domain. But in principle, you can do this for any constraint, right? If it was somehow easy to optimize over that constraint, then you could just plug it in, right, and solve this optimization, this constraint optimization problem explicitly, right? If you can do that, it often simplifies your life, right, because you're taking some of the constraints out of the problem. Okay, so those are just a couple different examples. We'll see. You get to see a lot more examples on the homework that you'll get to work through. They'll be a little bit more complicated, but not much. It's the same kind of ideas over and over and over again. And once you sort of see them a couple times yourself, I think you'll get the hang of it, and realize that there's really nothing too crazy going on in any of these situations. So the book does lots and lots of examples too. So if you wanted to see more and more examples of constructing dual optimization problems, chapter 5 in the book does lots and lots of examples. The caveat, if you're going to read through the book, is that the book does much more complicated examples than what I did in class. So some of them might require you to put your linear algebra hat on and think, you know, quite deeply about how you construct some of those things. In particular, if you really go to the sort of the end of the examples, you'll see that some of them depend on what are called something called the pseudo inverse. It's like something that always exists for it's like kind of like an inverse that always exists for every matrix. So again, you know, there's lots more examples there, but you know, you don't need to like, you know, internalize all of them, right? Once you do a couple of them, I think you'll get the hang of how this stuff works. Okay, in the last 10 or so minutes, I just wanted to talk, you know, kind of briefly about how you would use this dual procedure kind of algorithmically. So first, just a few practical comments. So where do people really use convex duality? So the places I've seen it used are, first to basically solve optimization problems by hand or transform them into a nicer optimization problem. Oftentimes in practice, the dual problem can have sort of nicer features that are not available in the primal problem. A good example of this, if you've taken a machine learning course, is that the optimization problem for support vector machines, its dual has some nice features that allows you to do like these infinite dimensional like kernel mappings. If you haven't taken machine learning, don't worry about that. There's lots of examples of this, though, right, of where the primal problem is somewhat complicated, but the dual problem is somewhat easier and or at least can be solved more easily with respect to a set of tools. Another good example might be that maybe the primal problem has a really complicated constraint set, but in the dual problem, the constraints are really simple, so it's easy to do projected gradient methods in the dual, and it's hard to do that in the primal problem, for example, right? So there's advantages to working in the dual then, right, because the projection is easy to compute or something. Oftentimes, the dual gives you nice insights into the primal problem, and as I mentioned before, you can use the dual for other nice things too, like if there's zero duality gap, right? You can the dual gives you a bound on the if you solve the dual and the primal problems, let's say simultaneously, then you can get a bound on the actual error of your estimator so far, right? You can compare the best thing you found for the primal versus the best dual, right? If there's zero duality gap, you know that those things have to go to zero, right, in the limit, and so you can get an error on your distance to optimality. So there's all kinds of different ways that people have applied duality to design algorithms. The first and sort of simplest way that you can use the dual in optimization, right, like with respect to some of the algorithms that we've seen so far, is that as an example, in some of the earlier examples we saw in class, right, if the dual has a closed form solution, you can always just form the dual optimization problem and then just directly apply whatever optimization strategies you want to optimize the dual problem. Now, remember that the dual problem is always a maximization problem. So technically, you would be performing a coordinate ascent in the dual. I mean, not coordinate, gradient ascent in the dual problem, right? That's equivalent to just taking the objective function in the dual and negating it and performing gradient descent, right? So the only difference between gradient ascent and descent is that in the gradient update, right, for gradient descent, right, you get the next iteration by taking a small step in the direction of the negative gradient. In gradient ascent, right, you take a small step in the direction of the gradient, right? The gradient is the direction of steepest ascent. The negative gradient is the direction of steepest descent. Right? So it's just a sign switch if you want to go from gradient ascent to gradient descent. If there isn't a closed form dual, right, like some of the examples that we saw today, you can actually still apply the strategy. Some of the strategies we've seen before, only you have to be a little bit more clever now. Not too clever though. So, as an example, we can always apply subgradient or projected subgradient methods to optimize the dual problem. So remember, right, that the dual is the infimum over all values of x of the Lagrangian, right, which is just this, weighted sum of constraint functions. So just like we saw in class, the supremum over a set of linear functions is always convex, right, and the infimum over a set of linear functions is always concave, right? That's how we proved that the dual function is always concave. So we saw on the last homework, right, you had a bit of experience, right, with computing subgradients of functions that were the supremum or the maximum of a set of other functions. So we can do the same thing here. We can apply subgradient methods to basically maximize the dual. So how does that work, right? Well, it works the same way that it did on homework 1, right? In order to compute a subgradient, which is technically, so we still use the term subgradient, but it technically is a supergradient here, right? The picture would be like for concave functions, the set of all linear overestimators of a function at a particular point is the set of subgradients, or they're technically gradients, right? Because they overestimate the function here. We still use the term subgradient, right? Because you can just negate the function and it's convex, and now it's subgradients. So the same terminology is used, even though technically they're not subgradients for concave functions. So to compute them, right, we solve this optimization problem, right? We actually compute the infimum of x over x. If this is if this always has a finite solution, right, we can use that to design a subgradient descent method. So it works like this, right? We have a fixed value of our dual variables lambda and nu. Given some fixed value, let's say at iteration t we've got lambda t and nu t, we solve that optimization problem, right? We minimize the Lagrangian over all x for a fixed lambda and nu. Again, the assumption here is that there is a finite x that achieves this thing, right? So I can write arg min instead of inf. So you find some x that minimizes that. We know that the subgradient then is just the derivative of the function evaluated at that particular x, right? So if I want to perform gradient ascent with respect to the lambdas and the nus, or projected gradient ascent in this case, right? I take the gradient of the Lagrangian, right, at the point xt, right, and that gives me a valid subgradient of the function. And then I just apply standard projected gradient ascent, right? So it's gradient, again, it's ascent. You notice that those are pluses instead of minuses. Okay. So it's a pretty straightforward process, right? The only kind of complicating thing is that we have to solve this optimization problem at every step, right? So unlike on the homework where they were all finite, it was like a maximum, not a supremum, right? Here, it's possible that there's something non-trivial to do, right? Unless we're sort of in special cases, like some of the examples we saw in class, where the derivative, right, basically has a closed form solution, right? That we end up with a Lagrangian that's a convex function. So when we take the derivative and set it equal to 0, we get a closed form solution for x. Right, so as an example, right, let's just do it. I just put together a simple example to illustrate this, like how this approach would work in practice for the projection problem that we saw earlier. A couple caveats about this method. Again, right, this really requires that the Lagrangian is bounded for all different values of lambda and nu. If it's not, this first step doesn't make sense. Right, and then you'll end up with like negative infinity as a subgradient, right? It's like having a horizontal asymptote thing at the function, right? At that value of lambda and nu. That's not very useful. You can't perform the rest of the procedure with something like that, right? If the gradient's negative infinity, you can't plug that in, right? It'll set lambda and nu equal to negative infinity, and then the whole thing just falls apart. The second observation about this method is that it doesn't guarantee that the sequence of x's that is produced is actually feasible, right? Because they're the result of minimizing Lagrangian, right? But that's an unconstrained minimization problem, right? So the Lagrange multipliers are acting as soft penalties here, right? But at no finite iteration, right, is it necessarily the case that xt will satisfy the constraints, right? So sometimes when these methods like this that are applied in practice, you'll, like as part of some like optimization toolkit or something, you'll see that in addition to a threshold that determines how well you've solved the optimization problem, there'll be also like some parameter that controls how well you've how well you've produced a solution that satisfies the constraints, right? So there's some like tolerance parameter for constraint satisfaction. So here, let me just show you this quick example, and then we'll end here, and I'll talk about one other method next time. Oh, I should point out one other thing. That what's the stopping criteria for this method? Well, it's a subgradient method, so there's not nice stopping criteria for that. You just run it for a bunch of iterations, again with standard step size choices, right? So it should have like a diminishing step size, right? The gamma t should be diminishing, but otherwise, it's the same kind of thing that we applied before. So here's how example how you would use it. So let's just take this projection on the box constraints, which we saw before. In fact, you could take any of the examples we did in class that had a closed form solution for the x's in terms of lambdas and apply this procedure. So here, it's easy to write down the Lagrangian, right? We started today's class with this. If you take the partial derivative of this thing with respect to x and set it equal to 0, you find that the optimal x has to be equal to p plus lambda minus mu. Okay. So the sequence of iterations for this particular trying to solve this optimization problem with that subgradient method would look like this. You set xt equal to p plus lambda t minus mu t. You then update lambda t to lambda t plus 1 by taking a step in the gradient direction. So the gradient of the Lagrangian here is simple, right? It's just if you take the derivative with respect to lambda I, you just get li minus xi. Right? So it's a simple update, and you have to project that onto the set of all lambdas greater than or equal to 0. The reason you have to do that, right, is because lambda and mu are Lagrange multipliers for inequality constraints, so they have to be greater than or equal to 0. So if you end up with any value for lambda or mu that's less than 0, you just fix it to 0. That's what the projection does. So I iterated it here a couple times in the slides, just so you can see what this process would look like. So if you started off with p equals 2 minus 1, and you'd like to project that onto the box defined by x greater than or equal to 0 and less than or equal to 1 with a step size of 0.5, again, you should pick a diminishing step size probably in practice. But here it will converge with it converges with a fixed step size because everything is kind of nice and smooth. But you get a sequence of iterations that looks like this. So here I started off with lambda and mu equal to 0, and my initial guess for the projection is just at 2 minus 1, which I get just by plugging in lambda equals 0, mu equals 0 into the equation for x 0, right? So 0 minus 0 is 0, so I just get the initial point p. Then as you iterate, you can see what happens is that at the first iteration, x isn't feasible, but after I just plug into the formulas, I get new values for the lambdas and the mu's, and the x slides a little bit closer to the projection. So it goes from 2 minus 1 to 1.5 minus 0.5 in the first iteration. In the second iteration, it's 1.25 and minus 0.25, etc. If I keep iterating this thing, it will converge to its projected point, which in this particular case is 1, 0. That's the solution. But you see, at any finite step, right, it might, the x is not feasible, right? It doesn't satisfy the constraints. It's sort of getting closer and closer to satisfying the constraints, but it doesn't actually satisfy them. So that could happen. It also could happen that you end up with something that does satisfy the constraints, but there's no guarantee that the iterations satisfy the constraints, right? Only sort of at the limit are you guaranteed to have something that does. Mm-hmm. Good. Okay, I'm way over time, so I'm going to stop there.